Okay, so previous speakers nicely summarized what we know about sulfide occurrences on Mars. It's everywhere, it's a sulfur-rich planet, and secondary sulfides especially are abundant on Martian surface. But we still have poor understanding of what the sulfide sources in past aqueous systems were on Mars, including Gale crater. And the main remaining question that we don't have a good answer yet is where did the sulfide come from? So previous geochemical models focused mainly on sulfide contributions from atmospheric deposition, and the sulfide formed in the atmosphere came from oxidation of emitted volcanic gases like H2S and SO2, and then has been deposited on the surface of Mars. There are some suggestions that maybe chemical weathering of sulfide minerals also contributed some sulfide into aqueous system in the past on Mars, but this atmospheric model is the most common cited in explanation where the sulfide sources could have been on Mars. It's a little bit different view on sulfide sources in aqueous systems of volcanic terrain that we have for Earth. In general here, atmospheric deposition on Earth contributes relatively small amounts of sulfide into aqueous system, and most of that sulfide comes from oxidation of volcanic gases that interact with aqueous system. There's a lot of formation of elemental sulfur, sulfide minerals, and then they undergo subsequent oxidation, and that's the major source of sulfide in volcanic systems on Earth. We have also formation of epithermal mineralization that can be sulfur-rich in the subsurface at much higher temperatures, and exposure of that mineralization later on into oxic environments on the surface also contribute quite high amounts of sulfide into aqueous system of volcanic terrains on Mars. The sulfur oxidation reactions in hydrothermal systems on Earth are very complex. In general, there is a lot of H2S gas that participates in those reactions. Generally, oxidation of H2S gas is very slow directly to sulfide. It rapidly forms, it gets partially oxidized and forms elemental sulfur and then sulfide minerals. And then once this is deposited in that surface aqueous system, then we have a subsequent oxidation of this elemental sulfur and sulfide to sulfide. And either it's oxidized by O2 or iron-free reduction, but in general, this oxidation pathway seems to be more important and contributes more sulfide, at least in hydrothermal features of wet climate. And then at higher temperature, and this sulfide, usually we can distinguish from other sources based on isotope composition of sulfide, like delta 34S value and delta 18O values are relatively low, often negative, and this source is very different from direct SO2 oxidation or SO2 disproportionation to sulfide that occurs in much higher temperatures. And this sulfide has much higher delta values for both sulfur and oxygen, and it forms in very high temperature environment and can contribute to sulfide formation. However, most of our information about those processes is from wet climates. We have less data to compare with dry environments that are more Mars-alike. So that's why with new project, last fall, we went to central Chile, to La Steria volcano that is located in the border of Chile and Argentina. And this is active volcano that releases a lot of sulfur. There's a lot of sulfur emission, H2S gas and SO2 gas. And around this volcano, in aqueous system on much lower elevations, has a lot of sulfate input from probably from oxidation of those volcanic gases, but then there's also a lot of older hydrothermal deposition, so we were interested about what kind of sulfate sources end up in this aqueous system in that dry region and drive precipitation of the secondary sulfate minerals. So we did sample La Steria volcano. There's a big hydrothermal field on the flank of this volcano. There's a lot of sulfur emission. we had to use gas masks because it was really intense H2S smell. And we took a lot of gas samples, also volcanic deposits, and then we also sampled this older volcanic bedrock that right now is inactive, but there is a lot of sulfur, hydrothermal sulfur mineralization from previous volcanic activity. And then we took water samples from those saline lakes surrounding Lasteria and salt crust to kind of see what actually contributes the most to sulfide formation in that aqueous system in dry environment. So here are our results. There is a large delta 34S variation in the system. The SO2 gas and H2S gas that are the major emitted sulfur gases have very different isotope composition. The sulfide and elemental sulfur that is forming from partial oxidation of that gas has also lower delta 34S values. And then when those end members get oxidized to sulfide, they preserve that initial isotope composition of those gases. So when we look at secondary sulfides that we collected on the slope of this volcano that are forming from oxidation and interaction with those gases, you can see that there is large delta 34S variation, and it seems that there are mixed proportions of sulfide from those different end members. And then when we looked at older volcanic bedrock, so all those red and orange areas here, we saw that sulfide also shows similar variation with mixed proportions of that sulfide that comes from oxidation of reduced sulfur and SO2 gas. And then when we looked at saline lakes, salars, called in Chile, you can see that there is distinctive isotopic variation. So the Azufrera lake, which is located in the closest proximity to Lasteria, you can actually see a little bit of that lake over here, had the highest delta 34S values of sulfide, which suggested that this lake receives quite big contributions of sulfide from oxidation of those SO2 gases. But then the inactive salars here had lower delta 34S values, and the lowest were in those places where we have a lot of hydrothermal sulfur-rich mineralization that undergoes right now chemical weathering in the interaction with snow and also occasional rain. So it seems that over time, you increase contribution of sulfide from oxidation of those hydrothermal sulfur deposits. We also had some samples that had very high delta 34S values that were indicative of SO2 disproportionation, but it seems that this is minor source and it was pretty far away from other samples. Here, this is another comparison of delta 34S value and delta 18O value. You can see that our samples, again, are between those end members, reduced sulfur end members on oxidation, and between sulfide that comes from that SO2 oxidation. We looked also at atmospheric deposition in this region. It was really hard to extract sulfide outside these volcanic zones from just atmospheric deposition, which suggested that sulfide inputs are minor. Also, sea aerosols that can be distinguished with those isotope tracers were farther away. We're still working on determining what are the sulfide inputs from atmospheric deposition, but they seem to be small. And then most of that sulfide comes either from oxidation of fumarolic gases. So here, this white belt shows you the sulfide with highest delta 34S values. And this is where fumarolic gases are pushed by the wind against the volcano slope, and this is where you see a lot of oxidation of that fumarolic gas. And then all those yellow colors here, this is where you have deposition and partial oxidation of H2S gas and formation of elemental sulfur that is yellow, but also orange color. This is indicative of increases of sulfide concentrations. And then when you take samples from those fumarolic fields and you extract secondary sulfide, it has a lower delta 34S and a lower delta 18O values indicative of oxidation of that hydrothermal deposit. So there are also older lakes in this area. We went 250 kilometers away from Lasteria in San Pedro de Atacama. Those lakes are at least few million years old. And they have really nice gypsum veins, which in some cases are very similar to what we see in Gale Crater. Right now we can study the subsurface of those playa lakes because they've been pushed up by the salt dome in the past. and were broken apart. And right now, these older lake sediments are tilting around this salt dome, and you can sample and have like easy access to those gypsum veins. So we took samples for isotope analysis to see what the sources of sulfide were for precipitation of those gypsum veins, because this is also a volcanic area similar to Lastaria. So you can see here that sulfide has the lowest values, delta 34S values, and it's indicative of more input from oxidation of that hydrothermal mineralization. And that's something very important for sulfide formation, at least for gypsum veins in that area. So the last slide comparison I would like to show you, I compared our data from Chile with samples that were collected in wet hydrothermal features, like in Iceland, Lhasa, and Yellowstone. And you can see that there is a difference in isotope composition, which is related to different sources of sulfide. And in dry areas, it seems that SO2 oxidation contributes more sulfide. The temperatures are much higher. And then in wet climates, that subsequent oxidation of elemental sulfur and sulfide in those hydrothermal deposits contributes more sulfide. So there is a relationship between climate and how much water is in the system, and that directly influences inputs of sulfide from those different volcanic sources. So to summarize, based on our initial results, we can conclude that there are two major sulfide sources in the system: oxidation of S-rich gases, especially SO2 gas, and then subsequent chemical weathering of these hydrothermal deposits enriched in elemental sulfur and sulfide. Atmospheric deposition seems to be minor in this volcanic system, and then we see important changes of sulfide contributions over time. It seems that with decreasing sulfur emissions, but continuing water activity, low temperature weathering contributes more sulfide into the system. So when we look at Gale crater, sulfide concentrations are the lowest at the bottom of the Mount Sharp. That kind of suggests that the groundwater that was discharging at that time probably was sulfide depleted, and that increases of sulfide concentrations might be related to that basaltic sand that was brought to the Gale crater later, and that could intensify, and it was enriched in hydrothermal minerals, and this could intensify weathering of those minerals and give you a lot of secondary sulfides in the system. So with this, I'm gonna finish, and there's some time for questions, I think. Thank you.
So if there are any questions, please come to the microphone and state your name and affiliation.
I found how to ask. So, you know, one of the issues we find with how this relates to Gale is that we haven't found any sulfides within the sediment. To be sure I understand, one of your scenarios you propose is that sulfide oxidized within the sediment to form the sulfates, or is it by analogy to Chile, or is it something else?
Yes, so sulfide has been actually detected in Gale crater. It's in lower concentrations. And sulfide weathers very quickly. I think after a long time of weathering, you would see decreases of sulfide concentrations. We see this in other areas. Here, also, if you have elemental sulfur, it's going to contribute. It will weather in a similar way to sulfide. And I know that recently that was announced that elemental sulfur is in Gale crater. So that's kind of, you know, this is what you would expect. A lot of sulfide when you have this enrichment in sulfur for chemical weathering.
And just one other question is,
yeah.
At the site, you show that those white streaks, is it sulfates or is it sulfur? Is it a mixture that we see are being wind transported?
So here, that white kind of belt, this is mainly sulfide, sulfate-rich salt. We haven't analyzed the sulfate for mineralogy yet, but the high delta 34S values really are indicative of that SO2 oxidation directly to sulfide. So that seems to be a main source of sulfide. And then you can also find a lot of secondary sulfides forming here, but they have different isotopic values, and they are more indicative of oxidation of this hydrothermal deposit.
Thanks.